Today I'm talking about something called the missing baryon problem. Baryons, if you weren't paying attention last week or didn't bother watching that video, that's fine. Baryons are the name astronomers give to normal matter, the matter like you and me. The thing is, we know how many total baryons there are in the universe, but we only see about half of them. Hence, missing baryon problem. Where did all the baryons go? A few years ago, we had a suspicion of where they might be hiding in the universe. A few years ago, we got some evidence that points in that direction, although it's not entirely confirmed. So let me tell you how we were able to make that measurement, how we were able to potentially find all these missing baryons. And yes, we checked the couch cushions, okay? We looked. They're not there. It's harder than that. When we zoom out to the very largest scales in the universe, so far out where entire galaxies are just tiny pinpoints of light, we see that galaxies are not arranged randomly in the cosmos. They have a pattern to them, something we call the cosmic microwave background, something we call the cosmic web. There are strings of galaxies, ropes of galaxies, there are walls of galaxies, there are dense knots of galaxies called the clusters, and then big empty regions called the voids. It looks kind of like a spider web, okay, but much larger. We've been looking for the baryons inside of galaxies and inside of clusters of galaxies. Clusters of galaxies have like 1,000 galaxies or more inside one of these dense knots. We had wondered if some of the missing baryons are in the filaments, are in those regions between the clusters, these long, thin ropes of galaxies. We see the individual galaxies, and we suspect there's some gas, floating along with them that aren't down in the galaxies, down in stars by itself. But because the filaments are very thin, they're hard to see. We just don't see them. We see the individual galaxies strung out like beads on a string, but we don't see the string itself. So to study this, astronomers used a technique that has an amazing name. It's called the sunyeav-zeldovich effect. It's two Russian scientists, Sunyeav and Zeldovich, Rashid Sunyeav and Yakov-Zeldovich, if I remember right. Two Russian scientists, two awesome names, one awesome technique. Here's the trick. Let's say light, low energy light, is passing through the filament on its merry way. We got some low energy radiation just minding its own business going through. And it passes through a filament, it passes through some of the gas in the filament. If that filament gas is hot, even if it's thin, if it's hot, if has a lot of energy, then the gas particles themselves will slam into the light. They'll bump into it. They'll knock it. They'll boost it. They'll give it some extra energy that it didn't have before. So that when that low energy light makes its way through the filament, it's going to be high energy light. It's going to have a higher temperature. So even though we can't potentially see the filament itself, we can see the effect it has on background radiation. All we need is a source of background radiation that soaks the universe, like, I don't know, maybe the cosmic microwave background. That light from the early universe, released when the universe was only 380,000 years old, is very cold, 3 Kelvin, 3 degrees above absolute zero. It's behind everything in the universe, hence the name background, and it covers every square inch of the sky. So that cosmic microwave background light, when we look at it and it passes through a filament, where that filament is, it will appear a little bit hotter. In principle. The thing is, the gas in the filaments is so ridiculously thin that this temperature bump is like barely negligible. You can't measure it. It's too small. But astronomers developed a technique. Have you ever heard the phrase, insanity is doing the same thing over and over again, but expecting different results? That's basically all of modern astronomy, doing the same thing over and over again, but getting different results. And here's what you do. You take one filament, you know where it is on the sky, and you put it here, and you take its signal of however it would affect the cosmic microwave background. You can't measure it because it's too weak. Then you take another filament, put it on top, another filament, put it on top, another filament, put it on top, and you stack filament after filament after filament, slowly building up the signal, not from one filament, but from all the filaments that you can observe. And using this technique a few years ago, astronomers were able to measure and map the gas in the filaments and begin to suggest that this is where all the missing baryons are, that they don't live in galaxies, that they don't live in clusters. They're not dense, but they are hot. They're in the filaments. They're just in these chains, these links, these highways between the clusters of galaxies in our universe. Otherwise, just minding their own business. The results aren't confirmed, but this is a good line of thinking because there's basically nowhere else for the baryons to go, because we already checked the clusters and they definitely don't live in the voids, because by definition the voids are empty. So yeah, if they're not in the filaments, we got a real big problem. Hope you like the show, and I will see you next week. And in the meantime, please go to patreon.com/pmsutter and keep those contributions coming. Thank you to all my space cadets for making these shows possible.